Today we will discuss about the stress. Stress is important topic because the stress concept comes in almost every subject of civil engineering. Today we will discuss the stress and how it is different from the pressure. So the main focus will be on the difference between the pressure and the stress. First, pressure. Pressure I will denote with P, and stress I will denote with sigma. Pressure is force per unit area, and it is Newton. Is force is Newton and area is meter square. So it is Newton per meter square, or 1 Newton per meter square is called 1 Pascal. 1 Newton per meter square is called 1 Pascal. In the same way, stress is force per unit area, and it is also Newton per meter square. Newton per meter square is called Pascal, 1 Pascal. From representation point of the view, pressure and the stress seems to be similar, but pressure and the stresses are totally different from each other. How these are different from each other, that we will discuss in this lecture. First, we will discuss about the pressure. Pressure. Suppose there is a surface and this is force acting on it, suppose F, and its area is A. Here pressure is equal to force acting on the surface divided by area. That will be the formula for the pressure. If this is the surface, the same surface of area A, and this is the force. Here the force is not normal, it is the inclined force. It will have two components, that is, if this is theta, this will also be theta. Here what will be the pressure? Pressure is force per unit area. Pressure is force perpendicular component of force divided by area, magnitude of area. Pressure is force perpendicular component divided by area perpendicular component, or pressure is force upon area perpendicular component. There are four possibilities. Which one is the correct definition of pressure? Pressure is force per unit area. Pressure is perpendicular component of force divided by area. Pressure is perpendicular component of force divided by perpendicular component of area, or pressure is force divided by perpendicular component of area. Here area is this surface. This is the perpendicular component of force, and this is the parallel to surface, and this is perpendicular to surface. This one will be F sin theta, and this one will be F cos theta. And this is total F. Here force will be the perpendicular component of the force will be used in the calculation of pressure. Therefore the pressure will be perpendicular component of force divided by area. Perpendicular component of force is, it has two components, it is parallel component and it is perpendicular component. It will be F cos theta divided by area. So pressure is component of force perpendicular to surface upon magnitude of area. That is the correct definition of pressure. That is the perpendicular component of force divided by magnitude of area. This is called the pressure. Therefore pressure is always perpendicular to the surface. But in case of stress, here stress is not always perpendicular to the cross section or plane or surface, because normal stress is perpendicular to surface, bending stress is perpendicular to surface, but the shear stress is not perpendicular to surface, it is parallel to the surface. Here also stress is force per unit area. Take example, if this is the body, and here it acts as the shear stress, suppose tau xy. So the complementary shear stress will be tau yx. These are the complementary shear stresses. Here if it is the surface, here the shear stress is parallel to the surface, and this one is perpendicular to this surface and parallel to this surface. That the stress may be parallel, it may be perpendicular. It is not always perpendicular to the surface, but the pressure will also be always be perpendicular to the surface. So the one difference between the pressure and the stress will be, pressure acts always normal to surface, but the stress may be normal or it may be parallel. Parallel in case of shear stress and normal in case of bending stress and direct stress. Stress may not be always normal to surface. That is the first difference between pressure and stress. Another difference between pressure and stress is, it is the second point. Pressure is a scalar quantity. Pressure is a scalar quantity, and stress is a tensor quantity. It is a tensor of degree 2, tensor quantity of second degree. Now what is tensor quantity, what is scalar quantity, what is vector quantity, we will discuss in deep in this concept. First, tensor. What is tensor? Tensor is a broad term. It is used for both scalar quantities and vector quantities. Scalar quantity is also a tensor quantity, vector quantity is also a tensor quantity. How these are tensor quantities, we will discuss. Tensor is a broader term which includes both scalar and vector quantities. Here tensors have degrees. First degree, 0 degree, 1 degree, 2 degree, 3 degree. These are the tensors. 0 degree tensor, first degree tensor, second degree tensor, and similarly third degree tensor. And so on, fourth to fifth degree tensor. These are all called tensors. It is also called zero order tensor or 0 degree tensor, first degree tensor or first order tensor. 0 degree tensor or 0 order tensor, it means any quantity which has magnitude and have 0 direction plus 0 direction. It is called 0 degree tensor. First degree tensor is magnitude and it has one direction. Second degree tensor, similarly it has magnitude and it has two directions. Third degree tensor has magnitude and it has three directions. Now, any quantity which has only magnitude but has no direction, that we call a scalar quantity. Any quantity that has magnitude but no direction is called a scalar quantity. Any quantity having magnitude as well as direction is called vector quantity. Vector quantity is scalar quantity. It is vector quantity. Hence, any quantity having magnitude but no direction is called a scalar quantity. Any quantity having magnitude and one direction is called a vector quantity. So the scalar quantity and vector quantity, these both are tensors. Scalar quantity is 0 degree or 0 order tensor and vector quantity is first degree or first order tensor. Here example of scalar quantity is distance. Example of vector quantity is displacement. Example of scalar quantity is speed. Example of vector quantity is acceleration. We are familiar with these two quantities, that is 0 order tensor and first order tensor. 0 order tensor is scalar quantity, first order tensor is vector quantity, because we have learned about these two quantities from 11th class. Now the new quantity is magnitude plus two directions. It is called the second degree tensor or second order tensor because it has two directions. It has magnitude and two directions, so it is called a second degree tensor. Here the example is stress. What is stress? Stress is force per unit area. Now we will discuss the stress. So stress is second order tensor, or it is second degree tensor. It is neither a vector quantity nor a scalar quantity. Scalar and vector both are tensors. Scalar is 0 order tensor and vector is first order tensor, but the stress is, it is second order tensor because we have to mention the two directions for defining the state of stress. Here I have mentioned it in the form of note. This is the general body and it is subject to general loading condition. Stress under the general loading condition. It is the general body and it is subject to any loading. It may be point load, it may be UDL, it may be UVL, or it may be torsional loading, any type of loading. Every body has three phases. This is x-axis, this is y-axis, and this is z-axis. The phase which is pointing towards the x-axis is called the x phase. Orange phase, it is pointing toward the x-axis. This is called the x phase. This blue phase, it is pointing toward the y-axis, so it is called the y phase. This pink phase which is pointing toward the z-axis, it is called the z phase. So there are three visible phases. One is x phase, y phase, and z phase. Every phase is subject to three types of stress. One is normal stress, and two are parallel stresses, that is shear stresses. This is also subject to one normal stress and two shear stresses. And the z phase is also subject to one normal stress and two shear stresses. So the every phase is subject to three types of stresses, out of which one is normal and other two are shear stresses. So stress has 9 dimensions. 3 is normal stresses, 1, 2, and 3, and 6 are shear stresses, with 2 shear stress on every phase. 1 is normal stress and these two are shear stresses. It is normal stress and these two are shear stresses. It is normal stress and these two are shear stresses. The normal stress is perpendicular to the phase and shear stresses are parallel to the phase. Now we will learn the sign convention, or it is called the nomenclature. I have mentioned here that normal stress or shear stress, the first coordinate and the second coordinate. The first coordinate, it represents the phase, and the second coordinate, it represents the direction. First coordinate is the phase on which the stress acts, and second coordinate is the direction in which the stress is acting. Take this. It is a normal stress on x phase in x direction. This is the nomenclature. This is the shear stress on x phase in y direction. Shear stress on x phase is the x phase and it is pointing in y direction. This is the shear stress on x phase, but it is pointing in z direction. Coming to this is the normal stress on y phase in y direction, and this is shear stress on y phase in z direction. This is shear stress on y phase in x direction. Coming to this is the normal stress on z phase in z direction, and this is shear stress on z phase in x direction because it is pointing in x direction. This is shear stress on z phase in y direction. It is phase z and pointing in y direction. This is the nomenclature of the stresses. This is the nomenclature of stresses. That is, the first phase will represent the first coordinate will represent the phase, and the second coordinate will represent the direction in which the stresses are acting. Now all the stresses acting on the body are represented in the form of matrix, and this matrix is called the stress tensor. Here it is the stress acting on x phase in x direction. This is normal stress. Shear stress acting on x phase in y direction. Shear stress acting on x phase in z direction. These are the three stresses acting on the x phase. These are the three stresses acting on the y phase, and these are the three stresses acting on the z phase. This is shear stress on y phase in x direction, shear stress on y phase in y direction. This is stress on y phase in z direction, and this is stress on z phase in x direction, stress on z phase in y direction, stress on z phase in z direction. The diagonal elements represent the normal stresses, and the non-diagonal elements represent the shear stresses. Here this is complementary to this, this is complementary to this, and this is complementary to this. These are called complementary shear stresses. And that means it is equal to this, it is equal to this, and it is equal to this. These are equal in magnitude but not in sign. That is, if tau xy is 5 kN per meter square, then tau yx will be minus 5 kN per meter square. That is, their sign will be interchanged, but the magnitude remains same. So this will be equal to this, this will be equal to this, and this will be equal to this. Here I have mentioned here, at any point stress has 9 dimensions. That we already learned that stress has 9 dimensions with 3 stresses on each phase. Out of the 3 stresses, one is normal stress and other two are shear stresses. So there are total 9 dimensions of stress. 9 dimensions or 9 components, out of which 3 are normal. 3 stress are normal and 6 stresses are shear stresses. But if I have to represent the stress on a body, the requirements of the stresses will be only 6, because if I know this, I know this, I know this and this, these are sufficient to define the state of a body. Because if I know this, this will be also equal to this, and this will be equal to this will be equal to this. So there are the requirement is only 6 stresses to define the state of the stress at a body. Here I have summarized all the differences between the pressure and the stress. The two major differences was the perpendicular and the tensor concept. Here stress may appear to be similar to the pressure, but it is totally different from the pressure. Stress is totally different from the pressure. First difference is stress is internal resisting force per unit area and pressure is external force per unit area. Stress is when we stretch a body. Suppose it is a body. If I will stretch this body, the internal force will resist this extension, and the internal resisting force per unit area, this is called the stress. Pressure is the force we will apply it externally divided by area is called the pressure. Pressure is external force and stress is internal resisting force. That is the first difference. Stress may not always be normal to the area, but pressure is always normal to the area. We have learned that the stress is not always normal to the area, because the shear stress is parallel to the area, and the pressure is always normal to the area. It is the basic definition of pressure. Pressure is what? It is the component of the force perpendicular to the area divided by the magnitude of area. So the pressure is always normal to the area, and stress is normal as well as parallel to the area. Another difference is stress does not lead to the pressure. स्ट्रेस की वजह से प्रेशर नहीं होता, लेकिन प्रेशर की वजह से स्ट्रेस डेवलप होता है. स्ट्रेस की वजह से प्रेशर डेवलप नहीं होता और प्रेशर की वजह से स्ट्रेस डेवलप होता है. यहाँ पे स्ट्रेस कैन नॉट बी मेजर्ड बट द प्रेशर कैन बी मेजर्ड. Pressure can be measured because atmospheric pressure can be measured by the barometer, and there are different devices to measure the pressure like manometers, but the stress cannot be measured. There is no device or no machine or no equipment that can measure the stress, because stress is the internal force. We cannot measure the internal movements, so stress cannot be measured. How? But we can calculate the stress. Practically what we do? Practically we measure the strain. If there is a body in the UTM is universal testing machine. We apply the extensions from here and here, the body expands and there is a neck formation somewhere here, and we measure the strain, and from Hooke's law we determine the stress from the Hooke's law. So stress cannot be measured, it can be computed from the Hooke's law. By noting the strain values, we can calculate the stress. Stress is not a measurable quantity. The last difference is the stress is the tensor quantity of second degree or second order, and the pressure is a scalar quantity. The stress is tensor quantity and pressure is scalar quantity. Scalar quantity is also a tensor quantity, but it is order and degree is 0. So the pressure is tensor of 0 order or 0 degree, and the stress is the tensor quantity of second order or the second degree. Therefore it has the stress has the magnitude, and we have to mention the two directions, that is x and y. So the stress is tensor quantity and the pressure is a scalar quantity. These are the differences between the pressure and the stress.